Okay, so in this video, I'm going to go through and discuss our periodic trends and how to justify um, differentiating between different elements using our specific justifications. I'm going to do this recording in two parts. The first one will be informational, and the second part will go through some more specific examples kind of in detail, just because it is kind of a lot of information to try to plug into one succinct video. So, first of all, the periodic trend is a systematic variation in properties of elements going down a group and across a period. So when we say group, those are your vertical columns on the periodic table. And we know, because we've already covered electron configuration, that everything in a particular column has the same valence electron configuration. So they do share a pretty good set of physical and chemical properties based on just that electron configuration. Going across the period, we don't see that same set of properties. These are all going to be different from their neighbor, because as they go across, not only are they adding protons, they're adding electrons. The electron configurations are then all going to be different. Okay? So we have two categories of trends. They fall into two main groups. We have size trends and we have energy trends. So when we're talking about size trends, we're just talking about the physical size of an atom or ion, how big or how small it is. And then our energy trends, we have three different types of energy that we're going to look at. So let's look at our size trends first. So our atomic radius trend is when we're comparing the size of two or more neutral particles. So two or more atoms coming from the periodic table. And we see that the general trend for size, for atomic radius, as I go down the table, the size of my radii increase. As I go across the table, it decreases. So the going down part should make good intuitive sense. As we go down the table, our principal energy levels are increasing. We know that means that the size of our concentric circles is continuing to increase. So it is going to get bigger. So if we look just at the 1A column on the periodic table, we know that this is primary energy level 1, 2, 3, 4, 5, 6, 7. One concentric circle is for sure going to be smaller than 7 concentric circles. So as we go down the table, it is going to get larger. The one that's a little bit less intuitive is that as we go across the table, the size of our atoms decrease. So as we go down the table, we're adding layers of electrons. But as we go across the table, we're just adding individual electrons. And remember that as I'm adding these individual electrons, I'm also adding protons. So the size of my nucleus is increasing. It's positive charge. And the electrons are being added no further away. We're adding the electrons to the same shell. And so because they're not being added any further away, they're being added to the same shell. As the nucleus is becoming more positive, the positive nucleus is going to attract those negative electrons and pull them in slightly. So as I go across the table, as I go across a period, I'm going to see the diameter shrink. So the radius becomes smaller. So those are for my atoms. So with ions, ionic radius, comparing the size of two or more charged ions, if we're looking at two different ions, we can use the same arrangement of trend. As I go down, I get bigger. As I go across, I get smaller. So for example, if I were to compare a beryllium +2 ion with a magnesium +2 ion, even though they're both positive ions, magnesium is still going to be bigger, right? It's got more layers of electrons, so it is going to go further down the table, and it is going to be a larger size. If I compare two ions going across, we know that oxygen most likely becomes a -2 ion and fluorine becomes a -1 ion. You kind of need to look at the ratio of protons to electrons. So when oxygen becomes -2, it has 8 protons and 10 electrons. When fluorine becomes a -1, it has 9 protons and 10 electrons. So if you consider the proton to electron ratio, you kind of think about it like a tug of war. The 9 protons is going to pull the 10 electrons a little bit tighter than the 8 protons will pull the 10 electrons. So fluorine will be slightly smaller than oxygen. So the size still does decrease going across. If I'm comparing an atom to its own ion, you need to remember how your ions form. So remember that if it's a negative ion is going to gain electrons, and so then it will become larger than its neutral atom counterpart. A positive ion is going to lose electrons, so it's going to become smaller than its neutral atom counterpart. And kind of a good rule of thumb is just negative ions are always going to be a little bit bigger. You have more electrons than protons. So if you think about that tug-of-war analogy I just made, the tug-of-war there is skewed in the direction of the electron. The electrons are going to be able to spread out more, and then you're going to have larger ions, Positive ions lose electrons, so that means I have an advantage on the proton side of our tug-of-war, pulling the electrons in more tightly. Okay, so those are our size trends. We'll get into the specific justifications of these when we get to the justification portion of this lecture. All right, so now let's talk about energy. So there's 3 different types of energy that we need to discuss. The first one is ionization energy. So ionization energy is the amount of energy required to remove an electron from an atom or an ion. How much energy is required to wrestle that electron away from the pull of the positive nucleus? Okay. The second trend is electronegativity. The electronegativity is the ability to attract a shared pair of electrons towards one's own nucleus. So it means for us to be discussing electronegativity, you really need to think about how this would behave in a bond, in specifically a covalent bond where electrons are shared. Is that atom going to hog the electron more, or is it going to lose custody more or less of that atom to its partner? And then finally, electron affinity. Electron affinity describes the likelihood of a neutral atom to gain an electron. So will it take on an electron? Does it really want to accept an electron? So all 3 of those trends follow the same trend. As I go across, the ionization energy, the electron affinity, or electronegativity and electron affinity all increase. As I go down, all 3 of those things will decrease. So these 3 trends are pretty closely tied to the size of the atom or ion, which is why you see that they're opposite that trend. So think about this, for example. As I go across, the size of my atom decreases, which means that the nucleus has a tighter hold on the electrons. So if I compare that with ionization energy is the amount of energy required to remove an electron. If the nucleus has a tighter hold on it, it should make sense that it takes more energy to remove it. Okay. As I go down and the atom gets larger, that outermost electron is further from the nucleus, meaning the nucleus doesn't have a very tight hold on it. So the amount of energy required to remove that electron is going to decrease. Okay, so again, you see how these are tied to size. Also, when you consider ionization energy, if you think about as this goes across and increases, the highest ionization energy you'll see on the periodic table is going to be with your noble gases, because it's very, very difficult to remove an electron from one of those noble gases. Remember, those noble gases are going to be over here on the periodic table in that 8A column. Electronegativity, the ability to attract a shared pair of electrons towards one's own nucleus. Well, if you are a very, very large atom, the nucleus is pretty far away. The nucleus isn't going to have a very strong pull on that shared pair, which is out in the valence section of the bond. So the bigger it is, the lower that electronegativity is going to be, because the nucleus is so far away. And then electron affinity is the same thing. It's the nucleus that really attracts the electrons in, because remember, electrons are negative, the nucleus is positive because that's where the protons are. If I have a very, very large atom, it's going to be hard for it to gain an electron because the nucleus isn't going to be able to attract those electrons in with all those layers of electrons in between the nucleus and that outermost area. Okay? All right, so now let's get into the justification part. How do I justify my choices appropriately? There are some specific terms and words that have to be used when you are justifying your selections of greatest and smallest using these trends. So the first one we're going to look at is if I'm comparing two things left to right. So within the same period going across. Doesn't matter what period we're in, but it has to be going across. I have to be comparing two things that are on the same level. Okay. So when I'm comparing two things on the same level, I'm going to use the justification of effective nuclear charge. Effective nuclear charge we also call ZEF. So what ZEF tells us is as we move, let me get to the bottom of this. There we go. As we move from left to right within the same period, we add more protons. Okay. Therefore, the nucleus gains a stronger positive charge. So the positive pull from the nucleus increases. The electrons are added also as we move across, but they're added to the same energy level. They are no further away. And because now the nucleus is getting bigger, it's able to hold them in more closely, more tightly. And so because they're held in more tightly, I can say, well, that's why, this atom is smaller than this one. Or I could also use that to justify why the ionization energy for this atom is greater than that one. So you can use ZEF to explain not only size trends going left and right, but energy trends going left and right as well. Because remember, the energy trends, a lot of that is dictated by the size. So let's look at an example here. Which is smaller, carbon or oxygen? So if we look at carbon's position on the periodic table, we look at oxygen's position on the periodic table. According to our trend, as we go across, we get smaller. So oxygen is going to be smaller, but we need to use our appropriate justification to say why. So oxygen is smaller. Okay, now we need to justify why. This was a left and right choice. So we are going to use ZEF to justify why oxygen is going to be the one that has a smaller radius. So oxygen is a smaller size than carbon. Oxygen has a greater ZEF, or you could write out effective nuclear charge, but a greater ZEF. Therefore, the larger, more positive nucleus holds the electrons more tightly, resulting in a smaller size. Okay. We could also change this and say which of these has the largest ionization energy. So it's still going to be oxygen, and the answer is still going to be ZEF. But when I talk about energy, I need to make sure that energy is a part of my justification. So how would I change this if I was talking about energy versus size? I would say oxygen has a greater ZEF. Therefore, the larger, more positive nucleus holds the electrons more tightly. And here's where you bring in the energy piece, requiring more energy to remove that outermost electron. That's what I would need to say if this was a question about ionization energy. Okay, so ionization energy is the amount of energy required to remove. The smaller the atom, the more energy is required. The more I've got to pry that electron away from that positive nucleus. And since oxygen has a bigger positive nucleus, it's going to take more energy to do that. Okay. All right. So that was left and right. Let's talk now top and bottom. So if I have an up and down situation, meaning I'm going to compare two things in the same column vertically, or maybe this column and this column vertically, like pretty close together horizontally, but definitely more of a vertical vertical separation. I've got two justifications I can use here. The one that is best, the one you're going to probably want to use more, is shielding. So when we talk about shielding, as you move down a group, the number of principal energy levels increases. Therefore, the outermost electron is protected or shielded from the positive pull of the nucleus, and the nucleus is not able to hold it as tightly. So let's kind of look at that in just a picture here. If this is my nucleus, when I say the number of principal energy levels is increasing, that means the layers. So if this is my atom, right? Energy level 1, 2, 3, 4, 5, 6. If I want to look at the pull of the nucleus as it tries to hold on to this electron in the 6th energy level, all of the electrons in these interior levels are essentially blocking the pull of the nucleus on this. So this one is really far away, and it's hard for the nucleus to control it, to hold on to it, to keep it as part of the atom. But if I were to look at something, let's say it only had 1, 2, 3 energy levels, well, now there's only 2 layers of electrons in between the nucleus and the outermost electron. It's a lot easier for the nucleus to hold on to that electron. So shielding is about how many layers are in between the nucleus and that outermost electron. How tightly is the nucleus able to hold onto it? The less layers in between, the more tightly it can hold on. The more layers in between, the less tightly it's going to be able to hold on. And that's going to be implicated in both size and energy, right? The more layers of electrons in between, the less tightly my nucleus can hold this electron, the bigger my atom's going to be. For this one, the fewer layers in between, the more tightly my nucleus is going to be able to hold on to that electron, the smaller it's going to be. If I go and think about energy, again, ionization energy is a good example. This electron is really far away from the nucleus. The pull of the nucleus on that electron is shielded by a lot of layers. So it's going to take less ionization energy to remove this electron because the nucleus isn't able to hold it as tightly compared to this guy. The nucleus has a closer hold on it. Only 2 layers are shielding the pull of the nucleus. It's going to require more ionization energy to remove that one. All right, so well, that leads us to a good example. Compare the ionization energy of magnesium and strontium. So let's look at our periodic table. So magnesium is here at 12. Strontium is down here at 38. So our trend is as we go down, our ionization energy decreases. Well, we know that as it goes down, it's also getting bigger, and my level of shielding increases. So I just need to tie that information together. So compare the ionization energy of magnesium and strontium. Strontium has a much lower ionization energy. I'm going to abbreviate that IE. Ionization energy than magnesium, as its outermost electron is more shielded from the pull of the nucleus and therefore requires less energy to remove. If I wanted to take this from the magnesium angle, I would just reverse all of those things. So I would say magnesium has a higher ionization energy because its outermost electron is less shielded. Therefore, the nucleus can hold it tighter. Therefore, it's going to require more energy to remove. Okay? All right, the next one is distance. And distance, to be honest, it's pretty similar to shielding. So it just says that the size of an atom increases as the distance from the nucleus to the outermost electron increases. I would use this more so for size than energy, because specifically with energy, you want to talk about the nucleus's pull, and that's definitely more of a shielding type justification. Whereas with distance, you're really just talking about, oh, it's bigger or smaller. So I could compare two things and say one's bigger than the other because in barium as opposed to calcium, right, the outermost electron is further from the nucleus because it's in a 6s versus calcium that's in a 4s. In calcium, the outermost electron is closer to the nucleus, so it's smaller. I would lean on this one the least. I would stick to Zeph and shielding as much as possible. Okay. All right. So those are our general trends and our justifications. The last thing that we need to look at is an exception, because what good is a bunch of rules if we don't have a monkey wrench to throw in with some exceptions? We are only going to look at one specific exception. There are more, to be sure, but in terms of this level of chemistry, we're just going to stick to this one particular exception. Okay? So we're going to look at an exception to our ionization energy trend. So just remember to review. With ionization energy is the amount of energy required to remove an electron. And our general trend is as we go across, it increases, and as we go down, it decreases. And we know that the reason that it increases going across is because the Zeph is increasing, the pull of the nucleus is increasing. As the pull of the nucleus increases, it requires more energy to remove that electron. Okay? This exception contradicts the trend in two specific groups in the P block, P3 and P4. So when I look at P3 and P4, remember what I mean is this is my P block. P3 is going to be this column here where nitrogen is, and P4 is this column here where oxygen is. So we're only looking at these two columns. Everything else, as far as you need to know, behaves as the trend dictates, but these two columns, right, do not. Right, and let's talk about why. So consider the electron configurations of the elements in the P3 and P4 column. If I wrote out the orbital diagram for P3 and P4, this is what I would have. In P3, I have 3 single standalone electrons, and in P4, I have 1 pair and 2 single electrons. Okay. So we talked about in electron configuration that when the electrons populate the orbitals, they populate across first so that we maximize the number of unpaired electrons, and then we go back and double up. And when those electrons fill in, they fill in with opposite spin because the opposite spin helps to minimize the electron-electron repulsion that exists because our electrons are both negatively charged. And so in this orbital, in the P4, I have a pair of electrons, and there is some repulsion that's existing between these two electrons. This electron actually repelled by this one and kind of wants to leave. Because if it leaves, then we go back to having this situation where we have 3 unpaired electrons, which is a energetically more desirable state. Okay? So although our P4 element does have a greater Zeph, and it does because it's going to have a bigger nucleus because it's further over to the right, the repulsion that occurs between these 2 paired electrons makes this particular electron in that pair a little bit easier to remove, which means the amount of ionization energy required to remove it is less. So even though I'm going across and even though my nucleus is getting bigger, it requires a little bit less energy to remove this electron as compared to this one, which is for sure opposite of our trend. Okay. So this exception holds for everything in the P3, which is our 5A nitrogen column, and your P4 6A nitrogen column. And it's all about that electron-electron repulsion. That electron-electron repulsion allows that one paired electron to be removed more easily. Now, when I go from P4 to P5 and comparing P4 to P5, I just continue with the regular trend. It's only between P3 and P4 that we are going to have this exception take place. Okay, so I'm going to go ahead and stop this video here. And then in the next separate video, I will go through some more examples where we can practice our trends and also practice our justifications.